This circuit is a voltage divider. It will divide the applied voltage into several smaller increments. This provides several voltages that can be used to operate devices requiring different values. For example, we could use one voltage to light a bulb, one to run a motor, or a combination of voltages to ring a buzzer. There's one problem, though. When these devices are connected, a number of changes occur in the voltage divider. We'll find out what these changes are as we discuss loaded voltage dividers. Let's use a different circuit and start by reviewing what we already know about voltage dividers. I'll remove the first trainer and put this one in its place, making the connections to the power source, and of course applying power. Now, we know that when components are connected in series like this, current will flow from the battery through each component and back to the battery. This develops a voltage across each component, and the sum of the voltage drops equals the applied voltage. Well, let's find out what the voltages are in this circuit. To do that, we'll use the PSM6 as a voltmeter. The function switch is on DC volts, and we'll use a range of 10. Now, we'll use the 10-volt range because the applied voltage is 12 volts, and this 12 volts will be distributed around the circuit as long as a reasonable amount of current is flowing. Okay, let's check across each resistor. And when using a voltmeter, remember, we must observe polarity. So across this one, let's call that 3 volts. Moving down to this one, let's call that one 4 volts. And this one, that's 5 volts. Now, of course, we can also obtain voltage from combinations of resistors. For example, if I measure across these two, we get about 7 volts. And across these two, well, it's a little bit over 9 volts, but we could call it 9 volts. We should also remember that different polarities can be obtained from a voltage divider. For example, if we were to ground the circuit here, all of the voltages in the divider would be negative with respect to this ground. If we move the ground up here, all of the voltages are positive with respect to ground. And if it's grounded anywhere in here, of course, we would obtain both negative and positive voltages. Well, in this lesson, we won't be concerned with polarities, but keep in mind that different polarities are available. Okay, let's use the voltage from the divider to do some work. Let me connect a bulb across this resistor. Now, when I make the connection, I load the circuit. Load means current. So when we load a circuit, we're demanding additional current from the power source. Of course, the component that we're adding out here would be called a load device. So keep in mind, load is current. The device that uses the current is called a load device. Now, this current or load creates a problem. It changes the voltages developed in the divider. For example, let's use the voltmeter to check the voltage across this resistor. And of course, I must observe polarity. So connecting across this resistor and the load device, we find that it's less than 2 volts. Now remember, we're using the 10-volt range on the voltmeter, and it's less than 2 volts. Now watch the reading as I remove the load device. It increases. It's about 5 volts. When I load the circuit, the voltage across this resistor decreases to something less than 2 volts. Well, let's move up to the other resistors. Let's do the same thing as we're checking the voltage across this one. Okay, with the load device connected, the voltage there is about, well, let's call it 6 volts. Now watch what happens as I remove the load. The voltage decreases to 4 volts. When I add the load device, it increases to 6 volts. So when we load the circuit, the voltage here increases. Let's go up and check this one. Observing polarity as I make the connections. Okay, with the load device connected, the voltage here is it's a little over 4 volts. When I remove the load device, the voltage here decreases. When I load the circuit, the voltage here increases. Okay, loading the circuit changes the voltages in the divider. Let me remove everything and we'll figure out why. Well, first, let's remember the voltage divider is a series circuit. But when we add the load device, we're placing it in parallel with the voltage divider resistor. These two components are in parallel. These two are still in series. And you know that adding resistance in parallel decreases the equivalent resistance here. If this resistance decreases, total circuit resistance must decrease. And we can verify this by using the ohm meter. So let's go to the PSM6, set the function switch to ohms, and we'll use a range of ohms times 10. Of course, anytime we're using the ohm meter, we must make sure that it's zeroed. And it is. Okay, I'll remove power from the circuit by opening this switch, and I'll take the load device out. Now, let's check the voltage divider resistance first with no load device on the circuit. I'll make the connections here and here. Of course, we're neglecting any meter resistance. Okay, this is the reading with no load device on the circuit. Now, watch what happens when I connect the load device. Total resistance decreases. Now, if total resistance decreases, current in the circuit must increase. Well, let's check this out. Let me remove the ohm meter and the load device and apply power. Okay, this is total current with the circuit unloaded. When I connect the load device, total current increases. Okay, the voltage in the divider changes due to a decrease in total resistance and a corresponding increase in total current. Now, to help clarify what takes place when a voltage divider is loaded, let's use a different trainer. Now, in this case, we're using bulbs instead of resistors, but we should remember that these bulbs do have resistance. Therefore, when the switch is closed, current flows and the applied voltage is divided among the bulbs. Now, let's load the circuit. When I make this final connection, down here, watch for a change in current. Watch for an increase in current. Okay, there it is. You can see that this bulb is brighter. There's more current through it. Well, let's look at it again. There's the circuit unloaded. When I load it, current here increases. And according to Ohm's law, if the current here increases, the voltage drop will increase. Now, this time, let's watch these two as I do it again. There's the circuit unloaded. When I load the circuit, these become dimmer. There's less current through them. Try it one more time. Unloaded circuit, when I load it, there's less current through these. With less current, the voltage here decreases. Now, of course, if we load the circuit more, the voltages in the divider will change more. The important thing is the voltage divider is no longer providing the voltages we started out with. Let's use this diagram and we can see this a little better. This voltage divider has two 6-ohm resistors and one 12-ohm resistor. The power source is 12 volts. With these values of resistance, the voltage drops are 3 volts across each 6-ohm resistor and 6 volts across the 12-ohm resistor. Now, let's add a load device that requires 6 volts to operate. It also has 12 ohms of resistance. we now have two 12-ohm resistors in parallel, so the equivalent resistance is 6 ohms. Essentially, then, we have a circuit with three 6-ohm resistors. This means the applied voltage is equally divided between the resistors. All of the voltage drops have changed. We're only providing 4 volts to the load device instead of 6 volts. We can obtain the required voltages with just a few changes. If we want 6 volts for the load device, we must have 6 volts across the rest of the circuit. Now let's look at this. We want 6 volts across 6 ohms here at the load device, so we must have 6 volts across 6 ohms in the rest of the divider. If we remove one of these resistors, like this, we've accomplished what we set out to do. We have 6 ohms here with 6 volts, 6 ohms here, and 6 volts. The applied voltage is equally divided across the two networks. Okay, we're finally obtaining the voltage we need. But let's think about this for a minute. We only get the correct voltage with one particular load. If the load changes, the voltage in the divider will change. Then we're limiting the use of the voltage divider to one specific load. Well, let's go a step further. Let's see if we can maintain a constant voltage under varying load conditions. Okay, this is the circuit. The key component is the control circuit. Its purpose is to maintain a constant voltage across the rest of the voltage divider, even with a changing load. We'll use bulbs to load the circuit, so I'll connect one here. Apply power to the circuit, and let's use the voltmeter to monitor the voltage to the load device. We'll have to change the function switch back to DC volts. We're still on the 10-volt range. Connecting the meter across the load device, we see that the voltage is about 6 volts. Now suppose that we need another light out here. In other words, more load on the circuit. Watch the voltage as we load the circuit more. Well, you see the voltage has decreased. However, as soon as the load starts changing out here, the control circuit detects this change. It changes resistance. Well, it's a little bit touchy, so let me get it right on 6 volts. It changes resistance and decreases the voltage across the control circuit. The decrease in voltage here brings the voltage to the load device back to 6 volts. Now let's see it again. I'll remove this bulb, which changes the load on the circuit. The control circuit reacts to that change by altering its voltage drop. When it alters its voltage drop, it brings the voltage to the load device back to its original value. Now, don't be misled by the control circuit that I've used in this demonstration. Actual control circuits are electronic devices that automatically react to the slightest change in the load. They react so fast that for all practical purposes, the load voltage never changes. Now, you'll study these control circuits and their use later on in the course. Okay, let's go over some of the things that we should remember about the loaded voltage divider. Remember, a voltage divider is basically a series circuit that divides the applied voltage into several smaller increments. Remember, though, when the circuit is loaded, all of the voltages in the divider change. Keep in mind that the voltage change is caused by a decrease in total resistance, which allows total current to increase. To get accurate voltages, you must know the amount of load you're placing on the circuit. Remember also that special circuits are used to maintain a constant voltage under varying load conditions. The voltage divider is one of the most versatile and commonly used circuits in electronics. You'll find them in equipment ranging from a small transistor radio to the most complex computer. They'll present no problem if you apply the principles we've covered in this lesson.